Okay? You got to get your calculators out, because what I want you to do is, I want you to, everybody has to calculate. Okay? Everybody has to calculate. All right? And what I mean by that is that you have to go through the mathematical operations. Clear? All right? You just have to do it, because otherwise you're not going to be used to this. Okay? So it says a metal cylinder, number 50, we're starting off with. It says a metal cylinder contains 1 mole of nitrogen gas. 1 mole of nitrogen gas. What will happen to the pressure if another mole of gas is added to the cylinder, but the temperature and volume do not change? The temperature and volume do not change. Will?
The pressure would double.
The pressure would what?
Double.
Why would the pressure double?
It's twice as much pressure, it's twice as much gas as the same amount of
Okay.
volume.
Aaron, what do you think? Did you look up that document?
Yeah.
What's on the Google Drive?
I can't find it on Sun Drive, but I'm not chemistry.
Is it in chemistry?
It's loading right now, but it's kind of slow.
It's not there?
The internet's not really. The internet's going kind of slow right now.
The internet's going kind of slow. Okay, so we're not sure what this is going to do. You're going to double the moles of gas. Okay, you're going to double the moles of gas,
Yeah.
and you're going to see what happens to the pressure, correct? Yes or no? Yes? And there's not going to be a change in what? Temperature or volume. Okay. Is there a relationship between moles and pressure that you're aware of that also has in it volume and temperature? Anything? Anybody know? Now let's get perspective here. You've read the chapter, you've outlined the chapter, you've done a lot of problems in the chapter, right? So let me ask that question again. Is there a relationship with moles, temperature, volume, and pressure that you're aware of? Antoine, that's absolutely correct. He's having a great day. That's very good, Antoine. Excellent. All right, 5 points for the Belgian team. Excellent. Well done. That's PV equals nRT. Okay. Now, yes? It's called the ideal gas law. Excellent. 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 I don't understand French, but I think that's what Antoine was saying when he was speaking and saying that he was trying to impress us with his French, and I was impressed. Very good, Antoine. Last time I spoke French, they had to rush me to the hospital. My throat closed up. The most difficult language, other than Arabic, of course. Okay? Typical American, I speak one language well. Okay. So, what does the equation say? Let an equation, don't think of the equation as the enemy. The equation is simply a sum of the concepts involved in the chapter. What does it say? What does that equation say about the relationship between moles and pressure in a container if the volume and temperature are held constant? R is a constant. It's called the ideal gas constant. So constant, constant, constant. So only pressure and moles are varying. What does that equation say about the relationship between pressure and moles? Well, they're directly proportionate. If they're on the opposite sides of the equation, they're directly proportionate. Let's look at something. Y equals 4x. If x is 2, y is 8. If x is 8, y is 16. As one goes up, the other goes up. Clear? It's directly proportionate. So if they're on the other side of the equation, they are proportionate. Clear? Easy? Yes or no? Okay. So the answer would be, the relationship is what would happen if you increase the number of moles, you're going to increase the pressure. Easy? Double, triple, quadruple, whatever the case may be. Okay? Mohammed, how you doing there? Are you all right? You having a better day? Excellent. You already look like things are improving. I like that. All right, number 51. It says, 51. It says, if a gas is compressed from 4 liters to 1 liter, and the temperature remains constant, what happens to the pressure? If gas is compressed from 4 liters to 1 liter, and what law is that based on? Boyle's law, and what would be the answer? You're gonna, it's gonna be 3 times, right? Right? You're gonna, oh, I'm sorry, what did I just give you the answer away?
It's 4 times.
What's 4 times? 4 times. Right, I'm sorry, not 3 times, sorry. I said 4 minus 1 is 3, sorry. Okay, I'm rushing this. You ever play fast golf or fast baseball or
Speed golf? I say run.
speed golf?
I think so.
Something like run from hole to hole.
Yeah, we would play speed golf when it was like in the late summer when it was like 6:30 and you're like on hole 7 and you want to get through all 18 and it's really exhausting. And you end up shooting better in some holes than you normally would. Like I'll get a hole in 1, but on the next hole I'll shoot a 40. You know, so my score will be a 400, but I'll be several holes under par. But several holes will be 40 over par. But I like it. Fast baseball, I like it. Okay, right. Now, so if it's going to go from 4 liters to 1 liter, okay, and then you're going to have the pressure is going to be, what's the pressure? We don't know what the pressure is that correct?
Yes.
So pick a pressure. You can pick any pressure you like. Pick a pressure. We'll say this is what? We'll say this is 1. 1 atmosphere. Okay? So what does this? What does that pressure have to be? 4 atmospheres, right? Because I'm going to cut the volume by a 4th. The only way I can do that is if I quadruple the pressure. And how do I know what the answer is? 4 times 1 is 4 divided by 1 is 4. So P2 equals 4. So if you quarter the pressure, quarter the volume, you're going to quadruple the pressure. Clear? Easy? All right, good. I'm asking. So stop me. Stop me if there's a question. Remember I said that this is going to be a lot of common sense. Okay? All right, what's next? 54. Right, it says the gas in a closed container has a pressure of 300 kilopascals. So always, you know, when the first pressure they give is P1. Second pressure is P2. Just make sure you put your data down. I'm giving you a fail-proof technique. All right. And then what does it say next? It says 300 kilopascals, right?
At 30 degrees Celsius.
And that's the temperature is 30 degrees Celsius. Is that what you said, Will?
Yeah, or 303 Kelvin.
Okay, well, let's hold off on that. Because I want to make a big deal out of that, okay? And it says, what will the pressure be if the temperature is lowered to negative
172 degrees Celsius.
172? Is that what it says? Yes.
Negative 172.
Negative 172, right?
Yes.
Negative 172. Is that right? Can you see that? Does that come up? Okay. All right. Let me move these down just a pinch so you can see the numbers that we're doing. Let's see. That says 50. There it is. Okay. Yes. Thank you. Well done. T2. Okay. Yes? Let me write that a little bit nicer. Negative 172. Okay, good. Yeah. So, what temperature scale must be used in gas laws? Antoine. Yeah, Kelvin. And why is that?
Is this easier?
It's easier. I think so. You get rid of that negative, that's for sure. Will?
It's the SI unit.
It's the SI unit. Okay. Yes.
It's more accurate.
It's more accurate. Absolutely. Yes.
Is it for both substitutes zero?
Yeah, the denominator can't be 0.
You don't
Can you divide by 0?
No.
Of course you can. Why can't you divide by 0?
It's undefined.
It's undefined. Excellent. Because we don't know what it is, but there's something. Yeah. But in other words, you know, you're going to go into the negative number, so there's still temperature to be lowered. The reason you don't have to worry about Kelvin is at 0 degrees you don't have anything anyway. There's no pressure, temperature, there's nothing, right? Okay. So what would this be? P1 T1 equals P2 T2. So it's going to be 300 over 303, 273 plus the Celsius, right? 273 plus 30 is 303. And then this will be equal to, remember, that's pressure over temperature. I left off the unit labels, I apologize. And then this will be P2 over what's negative 172 plus 273? 101. Right? And what's P2 equal to?
P2 equals 100 kilopascals.
100.
Yeah. 1.00 times 10.
Is that it? Is that the correct answer? Is it? Okay. Yes? Why don't you be our fact checker, Aaron? Go to the PowerPoint. Did you find the PowerPoint on the drive?
Yeah.
Okay, go to the PowerPoint.
Gas laws.
Yeah, and you're about 10 behind. You're about 10 problems. So in other words, if this is problem 54, go to around 44-ish. It'll be 8 to 11 behind, I think. I think if that's correct. All right, now, can we continue? Yes? So you need your textbook. Why don't you and Mr. Salmon Man do that? Okay, you can be our fact checkers. Okay? All right, now. What do we got next? We have 57. That sounds like a good one. A gas with a volume of 300 milliliters. Okay? A gas, 300 milliliters. Okay? Let's see. 300 milliliters at 150 degrees Celsius. What are you going to do right away? Well, I want to do this right away. What are you going to do right away? Yeah. Put it into Kelvin, right? Now, how do you do that? 150 plus 273 equals 4. What is it? 423. Why don't you use degrees? Why don't you do that? Because it goes down to 0, right? It's an absolute scale. You don't need degrees, right? And what's the size of the Kelvin scale versus the Celsius scale? What's the size of the gradation? Absolutely the same. As opposed to the Fahrenheit scale, which is about 1/8 as small, right? 1.8 is small, right? Ish, I think. Yeah. Okay, so, and then what does it say? What else does it say? It says, all right, okay. It's heated until the new volume expands to 600 milliliters. So it's going to expand to 600 milliliters, and they want to know they want to know what? T2, right? Is that the problem? Is that it? What's the new temperature? And let's make the temperature in Celsius, okay? So what would be the new temperature? So it's going to be V1 over T1 equals V2 over T2, and that's going to be what? 300 milliliters. I have something to say about that. Milliliters. Are we using milliliters? That's a little weird. Are those SI? I don't think so. Milliliters? We use liters, right? Isn't the ideal gas constant in liters? Yes. Yeah, so this is a little weird. This is a point of confusion, which is very easily explained. 423 Kelvin equals 600 over X over T2, right? 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 Okay, so what's the answer? What's T2 going to be? What's 423 times 600 divided by 300? Yeah. 846 Kelvin, right? You double one, you double the other, right? Now, Antoine, I'm picking on you today. It's a good thing. Say thank you, Mr. Dorsey.
Thank you, Mr. Darcy.
You're welcome. He's so polite. Okay. If you double the volume, you double the temperature, right? But are you doubling and you double the Kelvin, right? Are you doubling the Celsius? It's a little weird, don't you think? But I thought that a Celsius degree and a Kelvin degree is the same. What's that about? Let's look and see what it is in Celsius, okay? Subtract 273, right? To get it back, right? So what is 846 minus 273? Will?
573.
573 degrees Celsius?
Yeah.
So you're going from 150 to 573. Isn't that cool? Is that cool or what? Isn't that cool?
Radical.
Who said that? I like that. Radical. I feel like I'm back in the early 70s. Okay? Yes? You get it? Okay? Now, what's this thing with milliliters? Why can we use milliliters? Yeah.
It's just radical, but it's really
They cancel. Don't get crazy. You can use your grandmother's old phonograph if you like, because they cancel, right? They cancel. So it doesn't matter what you use. They're gone. As long as they're the same, I mean, you can't use liters and milliliters, but if you're using milliliters, as long as they're the same, that's okay, right? Temperature is the difficult one. Temperature has to be in Kelvin. Clear? Okay, good. What's next? 60? I'd like to get through at least half, plus do a hard one. You know, otherwise, because I want you to be able to work on these yourself. Like redo them, you know, put in some different data. Yes? All right. So, which one are we doing now? 60? Okay. 60 says a sealed cylinder of gas contains nitrogen. A sealed cylinder of gas contains nitrogen gas at 1,000 kilopascals. What's 1,000 kilopascals? Is that temperature, pressure, or volume? It's pressure, kilopascals, right? So P1 equals 1,000 kilopascals. How many pascals is that? A million, right? 1,000 times 1,000, right? 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 Neve, you with us? Excellent. Excellent. Okay. So, the temperature is 20 degrees Celsius. What are we going to do right away to that?
Kelvin.
Always put in parentheses next to it. You just save yourself. Trust me. Okay? You're talking to someone who made 10 zillion gas law mistakes as a kid. Okay, now. It says, when the cylinder is left in the sun, the temperature increases to 50, right? So P1, T1, 2. So I leave this in the sun, right? What's going to happen if you leave it in the sun? Constant volume. What's going to happen to the pressure? It's going to increase the pressure, decrease the pressure. Doesn't matter. Who cares? What?
It's going to increase the pressure.
You're going to increase the pressure. You put a can of beans on the stove and you don't open it and you light it. Don't you have enough experience on this planet, Red, to know what's going to happen? What's going to happen to the pressure inside the beans? It's going to increase, right? Okay? It's going to make a mess. Trust me, I tested it. Not in my house, like going camping. You got to do it. I mean, it's just part of the ritual. You know? The old beans test, right? Okay, so 50 degrees Celsius is what?
323 Kelvin.
What is it?
323.
323, you said? All right, so it's going to be 1,000 over 293 equals P2 over 323. What do you got? 1,000 times 323 equals 293.
1.1 times 10 to
What is it?
1.1 1 times 10 to...
Don't give me inside your invitation. Because it's not that high. I mean, it's going to be what?
1,100.
Is 1,100? Is that right? Yes? Okay, you all right with that, Mohammed? Does that meet your approval? Excellent. Okay, well done. Okay, now, can we push on? Number 67, is that what that says?
Yeah.
All right, we'll do 2 more easy ones and then we'll do a strenuous one. Kind of cool, actually. All right, you ready? All right, 67 says, if 4.5 grams of methane, CH4, all right, so let's put that down. So mass equals 4.5 grams methane. What's the molar mass of methane? Quickly. Jad, what did you say? Quickly. Take your time. Come on, take your time. Jad, quickly. Carbon is 12, hydrogen is 1, 4 times 1 is 4, plus 12 is 16. That's absolutely correct. Well done. Okay, so 16, right? AMUs, right? The molar mass would be 16 grams, correct? Excellent. Okay, good. Right. The pressure, volume, and temperature would be what? 67. 2 liters, right? We're looking for the pressure. The volume is 2 liters, and the temperature is what? What is it?
35 degrees Celsius.
35 degrees Celsius, which is 308. Is that right?
Yeah.
308 Kelvin. Is that correct?
Yeah.
And that was 35 degrees Celsius, right? Always put the change in parentheses. You got to do it. Got to do it. Understood? Yes. Okay, good. Now, what are we missing? What do we need? Yeah. But what piece of data are we missing? What is it? Shirishima?
It's use the ideal.
What is Shirishima?
The ideal gas.
How about? What is it?
8.31.
8.31 what?
I don't really understand. It's liters times kilopascals divided by Kelvin times volt. Whereas the confusion that I had was like putting that at the end of it, at the end of the like when you put
Those are the unit labels.
when you solve the equation, do you just put that as the unit?
I'll show you. That's a good question, actually. And what's on the denominator?
Kelvin times volt.
I like to put mol.k. Okay. All right, and I'll show you that in a minute. Okay. I'll clarify that. It's an excellent question, Will. Okay. Okay. All right. Now, so we know that PV equals nRT, right? And P will be nRT over V, right? So P equals 4.5 over 16. Isn't that correct? Isn't that correct? Isn't that the number of moles?
Yes.
Mass over mole molecular mass, mole mass, right? Times R, which is 8.31, times T, which is 308,
Yeah.
divided by 2. What do we got? What's P? What's P? Anybody? All these calculators, all this incredible calculating strength, Will?
I got, I'm not sure this is right, 4,555 point,
All right, I didn't hear you. You're like,
4,555.8744.
don't go crazy, because I'll have you arrested by the significant figure police.
87.
Okay, that's fine. I think is that correct though?
Point, the sixth one. It should be
Guys, can you plug this in? This is like about 0.5, right? What's 4.5 divided by 16? 0.25, 0.35. What is it?
0.28.
0.28 times 8.31 times 308
Wait.
divided by 2. What do you got? Do we have a fact check back there, Aaron? Are you ready for the fact check?
3.5
359.
or 3.6.
What's the answer?
259.
3.60.
I put the decimal place in the wrong place.
So we're talking 360, is that what you said?
Yeah.
And what are the unit labels on that? How do you know they're kilopascals?
Because they cross off. You got the liters, and you've got the liters. You use liters, and you
Oh,
use.
yeah.
Cancel out.
Cancel out.
Yeah, I mean, it cancels. And that's going to lead me to the next thing here. So kilopascals, right? All right, can I erase that now and just show you a little bit about the H, the R, I mean? Yes? Well, that R is really an experimental value. I'm going to let you read up on that, okay? So what you do is you say R equals PV over NT, right? Pick a value and then measure everything. Measure the pressure, the volume, the number of moles, the temperature at laboratory conditions. Put it all together, solve for R and see what it is, right? Now, you have to, you may be using atmospheres and not kilopascals, right? Can't there be various values for R, right? Depending on what you're using. Obviously, it's going to change, right? But aren't all those values equivalent? Of course they are. You could have atmospheres, cubic meters, moles, and Fahrenheit. Is it going to be 8.31? No. You could have this as whatever it is, experimentally. But look at what it is. Look at this. So this is kilopascals, liters, moles, Kelvin. There's where the unit labels come from. You see that?
But how do we write that at the end of an equation? Like you wrote 360 Kelvin.
All right, let's do it. Let's go crazy, okay? We'll do that, okay? We'll do that. We'll do the same problem, and I'll plug everything in, okay?
No, but like where did
I'm going to answer your question the way I understand it, and if I don't, ask your question again. But what I'm doing is not a waste of time. It will simply be complementary to what you're asking, okay? All right. So what were we solving for?
pressure. It's
Pressure, right?
yeah.
So what were the values? 4.5 grams over
16.
16, right? AMUs, or actually gram molecular weight, gram moles, right?
Yeah.
Right? Times
8.
V, right? No, nRT, right? No. Yeah, nRT. So it was what? It was 8.31. What are the unit labels?
L times, so liters times kilopascals divided by moles times Kelvin.
Divided by mole, Kelvin. And then what? Divided by?
Times 308.
Times 308
All over 2.
Kelvin all over 2 liters. Okay? Well, we know what the answer is, but let's get away from that, okay? Let's just put down the unit labels. So we're going to put moles. We're going to put liters, kilopascals over mole, Kelvin, right? Kelvin divided by liters, right? And that's in the numerator, right? Of the denominator, right? You get it? Right? Do you understand what I just did? It's important. Yes? Okay, in other words, this, yes? Okay. So, you need a little algebra understanding. Let me get right here. So, see how this mole cancels? Right? Yes? This cancels, because this is over 1, right? If you think about it. So doesn't this cancel with that? Yes? Doesn't that cancel with that? What are you left with? Kilopascals will, right? Now, this is what I do. And if you're good and you've done practice, then you don't have to worry about the unit labels. In other words, you've got to have something on the ball, right? Relative to doing practice. So I have listed P, V, N, R, T, right? If I know that this is in kilopascals, and I know this is in liters, and I know this is in moles, and I know this is 8.31, and I know this is in Kelvin, if I know all of that, right? I know all of that, then I don't have to use unit labels at all. Because I know they're going to fall out, right? But if I have, what do we use? We use kilopascals for pressure, and if it's not in that, put it in that, etc. Unless it's an application of like Boyle's law where milliliters will cancel or something, right? Yes, you get it? So it's not an issue.
We have to know the conversion formula, like PSI to kilopascals?
No. No, I don't think I have any conversion. The only conversion you have to know is Celsius to Kelvin and back. Okay. All right, shall we do 71? 71 should start to get a little bit hairy. All right, which gas effuses faster, hydrogen or chlorine, and how much faster? Excuse me. Yeah, go ahead. Hydrogen effuses faster. Absolutely. What's the rule? The smaller the gas, the more quickly it effuses. But how much faster? How much faster? So hydrogen's going to be. So you want the rates. Don't you want hydrogen over chlorine as your rates? Isn't that right? Yes or no? So you know that it's rate 1 over rate 2 equals M1 over M2, right? Shall I give you a hint? This will be on your test.
Ooh, whoa.
Exact same problem? No.
Mr. Darcy,
Yes.
in the book it says the square root of those that are both in the same square.
Okay, and you are in algebra or not? In other words, what's the rule? The rule says that root A over B equals root A over root B. No. Right? You can do it either way, whatever suits you. Okay? So, I know this is going to be hydrogen over chlorine because I want to know the rate of hydrogen compared to the rate of chlorine. And I want to know how many more times effusive the hydrogen is relative to the chlorine. So does it make sense that this is going to be R of hydrogen over R of chlorine? Yes or no? Okay? So let's go back to what Will said, because in this way it may be a little bit easier to visualize. This is going to be chlorine. Sorry. The molar mass of chlorine over the molar mass of hydrogen. Right? Yes? So what is it?
It's 35.5.
But take the root of it. Okay, so I understand. So 70-ish, right? Right? 70-ish over 2. Right? 70 over 2 is 35. What's the square root of 35, Neve? Estimate. Let me help you. Shall I help you? What's the square root of 36, Neve? I didn't hear you.
Square root of 65.
What is it?
8.06.
No.
Square root of 35 is
5.91.
6, so 5.92.
Okay.
5.91.
Okay.
5.92.
Neve, could you shut your book, please? Thank you. Okay. So what's the answer? I didn't.
5.92 times faster.
Okay, so it's 5.29 So, yeah, I mean, you're estimating it 6 times, right? Yes? 6 times faster, right? Okay? All right, good. So, easy? And that's a pretty difficult one. Okay? Now, right, let's do 74. Calculate the ratio of the velocities of helium atoms to the velocity of fluorine molecules at the same temperature. Calculate the ratio of velocities. How would you do that? You know what? Let's skip that one. Let's skip that one and let's go to a difficult one because I want to quit. Okay, I want to give you time to work on your stuff yourself. Okay? All right, so let's do number 94. Okay? And then we'll be done. 4 ammonia plus 5 oxygen. 4 ammonia plus 5 oxygen yields 4 nitrous oxides and 6 waters, right? Let me redo this. This is green. This is not going to come out very well. Right? So 4 ammonia and 4 ammonia, 5 oxygens, 4 nitrous oxides, plus 6 waters. Okay? Yes? Yes or no? Okay? All right, now. Let's put above them the masses. What kind of masses? The stoichiometric masses. What's 4 times 17? 68, good. And what's 5 times 32?
160.
160. And what is 14 and 16 is?
224.
So what?
224.
Times 4.
Oh, times 4, okay. 224, you said?
What do you want? Wait, 14 and...
Well, I don't know what you're giving me. I know that 14 plus 16 is going to be 30.
Plus 16, I thought you said times 16.
Oh, no, I'm sorry. I thought,
30.
okay. What is it?
14 plus 16 is 30.
It's 30, right, times 4.
Is 120.
120. Okay? And this will be what? 6 times 18?
Which would be 108.
108. Okay, good. Now, right. Let's do this now. All right, now, what does this say? This says, the problem says, when 34 grams reacts with how much oxygen? 96 grams, right? And then what does it say? What does it say?
What is the particular pressure measure?
What is the partial pressure? So if I have this much ammonia reacts with this much oxygen, yes? What's going to be the final pressure of just the nitrous oxide, correct? But are they going to all react, or are there going to be some excess left over?
Okay, maybe.
So, well, let's see. So this is going to be 4 ammonia over 5 oxygen is going to be 68 over 160 equals 34 over x. So 160 times 34 divided by 68 will be the amount of oxygen that will combine. So on your calculators, 160 times 34 divided by 68.
80.
What is it?
80.
80. Okay, good. 80 grams. So 80 grams of oxygen. Okay. Can we stop there in terms of what's limiting and what is in excess, or do you want to continue? What's going to be in excess, obviously? If you have an excess, you have the limiting. So what's going to be limiting reagent? Ammonia or oxygen? Ammonia, because this is in excess, right? Right? So this will all combine except for 16 grams, correct? Yes or no?
Yes.
You get it? Okay, now. So this will be 16 grams excess. O2. How many moles is 16 grams?
Uh,
32. You know that 32 is 1 mole. So 16 would be 0.5 moles, right? You get it? Or not? You get it? Okay, good. Now. Okay, now. So how many moles of ammonia reacted? How many moles of, no? 4 didn't react, you only had 34. If 4 moles reacted, 68 grams would have combined. But you only had 34 grams. So how many moles of ammonia reacted? 2 moles, right. What's the relationship between the moles of ammonia and the moles of nitrous oxide? What's the relationship? 1 to 1. 4 to 4, 1 to 1, right? So if 2 of this react, how much of this will be produced? 2. So this is 2 moles, right? Produced. Yes or no? Okay. Now, what are we looking for? Aren't we looking for the pressure of this? What other information are we given beside the masses of the reactant in the problem? We're looking for the pressure, right?
Yeah.
Okay, we're looking for the pressure, right?
Yeah.
Okay, so the pressure.
It's a 48 here.
Okay. And so what? Yes.
So a volume of 40 liter?
The volume of what?
40 liter.
40 liters, is that what you said?
Yes.
Okay, and the temperature of what?
393 Kelvin.
393 Kelvin. Anything else?
Parentheses.
That's it.
Did they give you 393?
Yeah. They give you it in Celsius, which is 120 Celsius.
Okay, so what? You get it or not? Do we have the number of moles? I mean, are there 2 pressures given? So it's not a combined gas law problem or a Gay-Lussac problem or anything else, right? Or Boyle's law, right? So it's definitely ideal gas, right? Because aren't we working with only 1 pressure, 1 volume, 1 temperature? Aren't we? So it's going to be ideal gas, right? So don't we have the number of moles? What are they? What are the number of moles? You told me. I didn't tell you. 2. Right there, remember? Yes or no?
Yes.
You get it? Okay, so put it together now. PV equals nRT. That's the equation. That's the equation. That's the equation that we're using. So it's going to be P equals nRT over V. P equals what?
P equals 2 times 8.31 times 393 over 40.
So that's going to be the pressure of NO, right?
Yes.
What is it? What's it going to be? What's the answer? Can I erase some of this? No, I don't need to.
163.3.
So this is going to be the partial pressure of that's going to be 163, kilopascals, right?
Yeah.
Now, what's the total at the end? What's the total at the end? What's the total at the end?
All of them together.
Yes, all of it together. What is it? How do you know?
Oh, it's the 0.5 mole.
Can't we do this? Can we use, aren't these values going to be the same? That value, and that value, aren't they going to be the same? Yes or no?
Yes.
Okay, so, isn't this going to be changing?
Yes.
So we can do partial pressures, but do we need to? What's the total number of moles that I'm going to produce? The total number of moles I'm going to produce is what? What's the total number of moles that I'm going to produce? What is it? It says low battery?
Yes.
Okay, well, I'm almost finished. Hopefully it'll stay lit. Okay. How many moles, total moles I'm going to produce? Well, isn't this 2 here? Isn't this 2 here? Half of that? What's this? 3. Right? 5 moles? Is that it? Nope. What do I have in excess that's hanging out? 0.5. So, what do you put here?
5.5.
Calculate it now.
Four 9.0. 0.1, sorry.
For what?
449.1.
Sounds right. Did we get, anybody else get that? You got it? Well done. That's it. Easy? Actually, a lot simpler than you may have thought. Yes? Yes? So which ones did we cover? We covered,
50 through 71 and 94.
we did these, right?
Yeah.
And this. Is that right?
Yeah.
Okay, good. All right, we're off. All right? I'll leave that on for a minute, then I'll shut it off.